So as I'm sure you've noticed, my last two lectures were quite computational. And that's not going to be the case for the next two. So my purpose is to make the next two lectures structural or constructional, if you wish. And the goal will be to show how certain structures of the algebra of symmetric functions and ultimately of representation theory produce probabilistic objects that are first interesting from the probability point of view and second analyzable from the asymptotics point of view. So what I tried to show in the last two lectures was what I meant by analyzable from the asymptotic point of view. Now, even though I can easily understand that if you didn't follow all the computations I was trying to do on the board, I hope that you will get the message that sure measures are ultimately computable. If you have a sure measure and you want to know some sort of an asymptotics about it, you can do it by reasonably modest analytical tools, something like classical steepest descent method. Okay? So this is really all I need for this and the next lecture for you to remember. Well, then, of course, the main technical tool that I will be using is the algebra of symmetric functions and different bases in it. If you were in TA sessions by Vadim Gorin, you've probably seen a lot of it, so I'll just do a 5-minute reminder of the objects that I will actually use. So the notation that I will use is capital lambda for the algebra of symmetric functions. That can be roughly thought of as the algebra of symmetric polynomials in infinitely many variables. It has a few bases. It has the basis, the algebraic basis of power sums, sometimes also called Newton power sums. So the algebra is freely generated by these power sums. Then there is also an algebraic basis of the complete homogeneous symmetric functions, which are, I'm not going to write the formula, I'll write the generating function, which is this. If you open up these geometric progressions and collect the coefficients of given degree, you get certain polynomials if the number of variables is finite, or symmetric functions if it's infinite. And then the algebra is also generated by these functions. Then we have the sure symmetric functions, which are, so these are sure symmetric functions, which form a linear basis, not an algebraic basis as here, but as the previous two, but these form a linear basis in the algebra of symmetric functions. They're expressed as polynomials in both p's and h's, and so in p's this is rather complicated. It involves characters of the symmetric group, but in h's the formula is fairly easy to write. Here is the formula. This is a determinant of size large enough, and with the understanding that h0 is 1 and h with negative indices is always 0. This is called Jacobi-Trudi formula. So you hopefully remember that I was talking about sure measures that were based on the Cauchy identity. So the Cauchy identity says that if I add products of two sure functions with the same indices over all partitions, so I should have said here that lambda varies over all partitions, finite sequences of weakly decreasing numbers, then the sum can be computed. I'll write this in the form as e to the sum of Pn of x, Pn of y over n greater or equal to 1, where Pn's are the power sums. So the sure measures assigned to a partition, the probability which was I will use the notation, so I will call this h of xy. I'll probably explain why. So if I normalize by it, then this is a probability measure. Now, the one thing I should comment is that, so this is really an algebraic object. This is an element in some algebra. And if you want to interpret these as numbers, you need to assign, the way of assigning numbers to symmetric functions. So this is achieved by something called a specialization, which is just a map from the algebra of symmetric functions into, generally speaking, complex numbers, which is an algebra homomorphism. So that means that this map respects addition and multiplication, right? One possibility to specialize is just to take the variables x's and assign numbers to them. Each of them is a number. If all the series converge, which is easy to do, then this is a specialization. But then there is an interesting question of classifying all specializations that are meaningful. Now, what do I mean by meaningful? So there is a meaningful problem of classifying something that I will call positive specializations, which are maps such that, okay, so I'll use the notation that the function f is being mapped as f of rho. So positive specialization is such that the values on all symmetric functions are non-negative, on all sure functions are non-negative. And you see that if this satisfies, if rho satisfies these inequalities, then the sure measure is an actual probability measure, right? So this guarantees that those weights there are actually positive. And the problem of classifying positive specializations is a deep problem. It has at least two different reformulations. It was first solved by Adrey in 1953 under the title of classifying totally positive sequences. I'm not going, well, I'll explain later to you what it means if you want, but I'll give the answer. So first of all, I'll give the answer. So the answer is that rho is positive if and only if I consider the generating functions of h's t to the n greater or equal to 0, then this needs to have the following form: e to the power gamma t, the product 1 plus beta it, 1 minus alpha it, over all indices I, where alphas, betas, and gammas are all non-negative, and the products need to converge, clearly. We can compare this expression to this expression. So if the specialization is such that you just assign numbers to x's, then this is responsible to these alphas here. But this is not it. There is also a way to put betas in, and there is also a way of putting gamma in, which is, so gamma is actually equivalent to the limit transition to Plancherel measures that I've done last time. Okay, so this is, as I said, there is an analytic work at Adrey, and there was in 1953 there was a work by Thoma who solved the same problem under a different name. He classified characters over the infinite symmetric group. He had no idea the problem is connected to Adrey, and was using different tools. And then finally, Vershik and Kerov, in the end of 70s, I guess the papers may be, I don't know, 1981 maybe, they realized that the problems are connected and presented their own approach to the problem. This is really a sideline. I'm not going to talk about this at all. I just wanted to tell you how to specialize sure functions to make the measure positive. So the key thing that I will also need today is Q sure function. So this Q sure function is parameterized by two partitions, lambda and mu. So it's 0 if mu is not contained in lambda. So if this is a Yann diagram of lambda, then the only non-trivial situation is when mu is strictly inside. There are several, right, and when mu is empty, then this is just the usual true function. There are several definitions that one could give. I'll give two. So one is the following. you take a Schur function in a set of variables x and y. So if I just take the alphabet and I name the letters in two different ways, and then I want to treat this thing, so it's a symmetric function in both x's and y's, and I want to treat this thing as a symmetric function in x's only, then I can decompose it in some way into symmetric function in x's, but then there will be some coefficients that depend on y. So these coefficients are the skew Schur functions in y. Okay? So this is the sum over all mu, which are ultimately going to be inside lambda. This is one definition. And then the second definition is that if I want to compute the Schur function, then I can just write it as a polynomial in terms of h functions. So this is going to be the analog of the Jacobi-Trudi formula. And then this is very similar. This is h lambda I minus I minus mu j minus j. You can see that this is actually the minor of a Toeplitz matrix. And this gives the relation to the totally positive sequences that I was talking about before. It happens that if rho is positive, it's not hard to show that actually it also gives non-negative values on all skew functions as well. So I'm going to generalize now the notion of the Schur measure to something that's called the Schur process. It's a much more powerful object whose marginals are Schur measures. So let me tell you what it is. It will live, so the Schur processes will live on sequences of partitions that I will symbolically denote by the following picture. So this is an empty partition. This is a partition lambda 1. This is mu 1, lambda 2, mu 2, and so on. The last one will be lambda n, and this is empty. The arrows mean that the partitions are ordered by size. So the diagram of mu 1 is a subdiagram of lambda 1, and so on. And if, so I need to write the weight of such a sequence of partitions, and then I'll write it as follows. I'll put a Schur function on each of these arrows, and then I take the product of them. Let me write the definition. This is going to be S lambda 1 of rho 0 plus. I'll put different specialization. So each arrow has its own specialization that I will denote by rows with various indices. So let me write the rho 1 minus S lambda 2 over mu 2 rho 1 plus, and so on, S lambda n of rho n minus.
What do you say again? When we go from lambda to mu, we lose cells, and from mu to lambda we gain cells. Is that correct?
Well, if you go along, right. So if the diagram is higher than the other one, then it's larger than the lower one. Okay. So this one is larger than these two. Okay. So that means that I'm using rho 0 plus here, and plus just means I'm going up, and then this is rho 1 minus, rho 1 plus, and so on, rho n minus. Just a trivial remark, if I just consider a picture like that, then this is a Schur measure. I put, let's say, specialization x here and 1 y here, and this is the product of S lambda of x times S lambda of y. So this process with n equals to 1 is just a Schur measure. Now, why is this a good object? Well, first of all, I haven't defined the measure yet. I just assigned the weight. The first thing one should ask really is whether I can compute the partition function, right? Whether I can add all these weights. Is there an analog of the Cauchy identity for this object? And well, this is sort of a principle of statistical physics. If you have some sort of weights, if you manage to compute the partition function, then your object is, your measure is likely to be analyzable at least partly. So the first question, whether this can be done. Now, the answer is based on two identities. So let me write those identities. here is 1. This is sum over nu, kappa over nu in row 1, S nu over tau in row 2 is equal to S kappa over tau row 1, row 2. So what is written here is actually a trivial corollary of one of my definitions of the Schur function that says the following, that if I draw a picture, if I draw symbolically what I'm trying to write, so I'm going down from kappa to nu using row 1, that corresponds to this Schur function, this skew Schur function. So then I'm going down by row 2, and I'm summing over nu. And this is the same as going from kappa to tau directly using the union of two specializations. So the union of two specializations really just, if the specializations are into values of x's, then this is just combining two sets of variables. That's all it is. But generally speaking, I can define the union of two specializations by saying that pk, the power sum, corresponds to the sum of the two, and that's literally just the fact that if I have two sets of variables, and if I take the power sum of two sets of variables, then, well, then this is the x sum and the y sum. And so this identity is kind of a triviality. Now the second identity is a little harder. Not too hard. I'll also draw a little picture to show how it works. This is equal to h row 1, row 2. So h, I remind you, this is this partition function for the Schur measure. And then this is the sum over tau s nu over tau row 2, s nu hat over tau row 1. So in pictorial language, this is the following. So in pictorial language, this is the following. I have kappa that sits on top of nu, and on top of nu, and on top of nu hat. This is row 1, and this is row 2. I am summing in kappa, and what I'm claiming is this is equal to a constant times nu over tau row 2, row 1, nu hat, and I'm summing over tau. Right, so these two diagrams, nu and nu hat, are fixed. I'm summing over something larger than both, and this can be rewritten as summing over something that's smaller than both. Okay? This is called skew Schur identity. It becomes Schur identity when both nu and nu hat are empty. If I kill nu and nu hat, then I get here the left-hand side of the Cauchy identity, and then this sum will become empty because there are no diagrams that are smaller than the empty one. So this is just this is the generalization. In fact, this identity can be obtained from, so it can be obtained from, sorry, I'm lying. This should be skew Cauchy identity. That's the wrong name. Skew Cauchy identity. It can be obtained from the usual Cauchy identity by something called co-product in the algebra of symmetric functions. The algebra of symmetric functions carries the structure of the Hopf algebra, and if one applies co-product to the Cauchy identity, one can recover. I'm not going to do it. If you're curious, you can look at the wonderful book by MacDonald called Symmetric Functions and Whole Polynomials, but I'll just use it. Okay? So I'm claiming that by having these two identities, I can compute the partition function over there. So how do I do it? I just erased the picture. I started with a picture like this, right? And this was lambda 1, mu 1, lambda 2, and so on, lambda n. Now then, what I want to do, I want to take this picture and I want to sum it over all lambdas. Right? So then the first thing I'm going to do, I'm going to take this mu 1, and I'm going to flip it to something that's going to be larger than lambda 1 and lambda 2, using this identity. Here. I'm summing over something that's smaller than 2 diagrams. I can flip it and put it on top. Right? So reading this backwards, I take this thing, move it on top. Now then, the picture will have, there will be some new, let's say new here, and so on. Then, when I look at this picture, I can contract over these 2 diagrams using this identity. Right? Something in the middle can be contracted. Then I get the up and down chain, which is one by one symbol smaller. And then I can repeat. That's all. So the inductive repetition of these 2 identities actually gives the answer that the sum W of lambda mu over all lambda and mu is equal to the product I less than j, h rho I plus rho j minus, where these are the specializations sitting on the, right, the way that's written there. So then the definition of the Schur process is, so then Schur process is that the probability of such a sequence lambda and mu is the weight of lambda mu divided by this partition function. Let me call it z. And then if I take my rows to be non-negative, then this is necessarily a probability measure. Okay? I'll try to explain why these probability measures are useful. Before I do that, here is another structural property. So the projection of the Schur process to any lambda. So if I take this measure defined like that, and if I just forget about everything except for a single diagram, and this is a Schur measure, is a Schur measure that corresponds to 2 specializations. Schur measure has 2 specializations, right? X and Y in the top line there. And these specializations are just unions of so the 2, okay, so this is going to be a Schur measure. I'll denote it like that. The Schur measure and the 2 specializations are going to be rho plus 0 j, okay, to lambda k, so k minus 1. And the second specialization will be rho minus jn, where this just means that I take the union of all rho minuses with indices varying from j to n. Okay? And this is easy to obtain just doing this inductive argument that I've done, summing over all diagrams, except for there will be some diagram lambda k in the middle that you're not summing against. And in the end, this will give you the answer.
And j is of course k.
And j is of course k, yes. Thank you. All right. The projection to mu actually will give a slightly different Schur measure. Yeah, please.
Sorry, in your formula for the weight, the third term is correct.
In my formula for the weight, what?
The third term is correct.
The third term, let's see. So maybe it's incorrect. So the picture looks like that. Rho 0 plus, rho 1 minus, rho 1 plus, and so on. So the first term is this arrow correct? Lambda 1 to mu 1 with rho 1 minus is correct. Yes, it's lambda 2 mu 2, lambda 2 mu 1. You're right. This should be to mu 1, rho 1 plus. This is true. It's easier to think in terms of pictures than in terms of indices. That's the reason I'm drawing pictures. Okay. So why are Schur processes useful? Well, first of all, Schur processes are analyzable in the same sense as the Schur measures are. Namely, sure processes can be described as determinantal point processes. I'm not going to do that, nor I will try to analyze any of them explicitly, but I'll tell you that by arguments similar to the ones that I presented last time, one can prove that. Now instead, I'll give you examples. Okay? So here is example 1. Now, example 1 will be plane partitions. Now, what is a usual partition? Well, I already said many times it's a weakly decreasing sequence of numbers. There is a way I can do it, which is a weird way, which is I take a line, I split it into segments of length 1, and then I inscribe lambda 1, lambda 2, lambda 3, and so on. And eventually you get zeros. So this is sort of a linear partition. Now, a plane partition is the following thing. Well, actually, I probably want to draw it in a skew way. So instead of starting with a line, I start with a region in the grid. It doesn't need to be a quadrant. It's just simpler for me to draw a quadrant at the moment. And then I inscribe numbers. 10, oh, well, okay, 2 large, 5, 3, 2, 1, 1, 0, 0, 0, 0. So the condition on these numbers should be the following. They should weakly decrease in both directions. And they should eventually become 0. Okay. So if this is too abstract, then you can think in the following way. You can think of these numbers as being values of a function. And then if you draw the plot of this function, then it will look like that. So this would be a column of 1, 2, 3, 4, 5. So this is the column corresponding to this 5. And then next to it, you have a column with 2 boxes. So I need to start on the floor, and then I have to grow column with 2 boxes next to it. And then there is a 3 here. So what am I going to do? I'm going to put another column here of height 3. And then there is a 1 and a 1. Well, that should be hard. So let's try. There is a 1. And there is another 1. Okay. So this is supposed to be a 3-dimensional picture. Let me try to paint it a little bit. I don't know. So let me paint the horizontal faces, for example. So this is another way to think about a plane partition. Right? Now, these plane partitions may be random, and it's a natural question to ask what can be said about random plane partitions. So let me, so what measure does one put on plane partitions? One variant to put a measure is just say I consider plane partitions of size 1,000,000 with 1,000,000 boxes, and the measure is uniform in all of those. It turns out that such a measure is not so great. It's not integrable or analyzable, but one can do something very similar. So if I say that the probability on a plane partition is proportional to Q, where Q is a parameter, raised to the volume. So the volume should be clear. It's the number of boxes I used to build this picture. It's the sum of all these numbers. Then the measure like that is nice. And the reason it is nice is because it's a sure process. Okay? Let me try to convince you that this is a sure process. So for that, I'll just do a baby version. I'll just take a square 2 by 2, and then I take, let's say, A, B, C, and D. It's great to equal, and these 2. And so I have a measure on these arrays, which is proportional to this. I want to see this as a sure process. Right? How am I going to do that? Well, first of all, I need to turn the plane partition into a sequence of ordinary partitions. So I'll do that by taking the diagonal sections. So this is going to be my first partition, lambda 1. And it just consists of one number b. This is lambda 2, and this is a comma d, and this is lambda 3, and this is c. Okay. So now if I write the following expression, s lambda 1 evaluated at something, I don't know what yet, s lambda 2 over lambda 1 evaluated at something else, and finally s lambda 2 evaluated over lambda 3 at something else, and s lambda 3 something else. So this is the picture the picture is lambda 1 is greater than empty, and then lambda 2 is even greater, and then this is lambda 3, and this is finally empty. Right? So now I will try to put the specializations inside so that the sequence will be in one-to-one correspondence with such an array, and the measure will be the one I need. Right? So for that, I need a effect about skew-sure functions that I haven't stated yet, but I believe Vadim should have. So the fact is the following, that if I take the skew-sure function and evaluate it at a single variable, so this is a single variable, everything else is 0. I just substitute a single variable. Then this is either 0, okay. It's either c raised to the power number of boxes minus, in lambda minus the number of boxes of mu, if the two partitions interlace. The coordinates must interlace, or it's 0 otherwise. Now, if you look at diagonal sections of plane partitions, you see that the condition of monotonicity is exactly that these diagonals interlace. Right? So that part is good. Now, finally, I need to be able to assemble this thing out of constant raised to the power. Right? So I need to put some constants here so that this works. Well, let's see. What if let me do something arbitrarily, sort of arbitrarily, and then see how it works. So I'll put first, so I'm putting on these two edges q to the half and q to the half. Now what it is doing, so when I evaluate it, it will give me q to the half the number of boxes in lambda 2 minus the number of boxes in lambda 3. And this will give me q to the half the number of boxes in lambda 2 minus the number of boxes in lambda 3. So when I add these two, I get q to the number of boxes in lambda 2, which is good. And then what about lambda 3? Now I have minus half the number of boxes of lambda 3, and ultimately I want q to the number of boxes there. So I'll put q to 3 halves here, and q to the 3 halves here. Then this gives me q to the 3 halves the number of boxes in lambda 3, and q to the 3 halves number of boxes in lambda 1. When you add them up, you'll see that I get q to the sum of the number of boxes in all partitions, which is this. Okay. And the argument is very general. It works for plane partitions in much more general regions. Namely, if I take a quadrant and I change the border of it by something, and then I consider plane partitions in a region like that, and I inscribe numbers and take q to the volume, then this is a special case of the Schur process. Now this observation and the notion of the Schur process is due to Kunko-Vershetikin back in 2003, I think, who actually analyzed the asymptotics of this corner object and obtained the limit shape in parallel with the work of Kenyon Cerf. This was a breakthrough in the study of three-dimensional Young diagrams. But this is really not my focus. I just wanted to mention it as an example. Let me do a second example. Example 2. This will be reminiscent of what I was doing yesterday. I will be using this Robinson-Chanstedt correspondence, which I'm not going to explain because I will substitute it with something later, but I'll use it to define what I'm doing. So if I consider random words built from an alphabet with n elements in it, with letter J appearing at the end, according to a Poisson process with rate AJ. So you have you start writing letters. I don't know, 3, 1, 5, and so on. And when there is no, you are building it in continuous time. And so when the next letter appears, then the appearance of the following one is random. Each of the letters has its own clock. That clock has certain rate of ringing. And the first clock that rings wins this position. Okay. So then you're just adding letters at the end of this random word. Each letter is being added independently with its own waiting time. Then, because everything is independent, the distribution of the probability of the length of the word is just Poisson with the distribution with the rate given by the sum of all the rates. 1 t to the power k over k factorial. So this is at time t. Let me draw it in a picture. So the picture that's associated to it is the following. I draw a strip of width n. It's 1, 2, up to n. This is my time axis. And then I'm going to record the events of the letters appearing by putting a star in the corresponding row. So let's say that 3 appeared at some time moment. So this is the appearance, this is T1, the time of the appearance of the first letter. And then the next letter is 1. It appeared, so I put a star here. It appeared at some time moment T2. And then the next one is 5, so there is a star here. And so the word, the whole history of building the word is encoded by this array of stars. Now, in each of these, so each of these strips of width 1 is independent of the rest and is a Poisson process, right? Just a one-dimensional Poisson process with rate A1, A2, A3, and so on. Right? Just a pictorial representation of the same thing. So then there is a one can do this. Something that I haven't explained how to do. this Robinson-Chanstead algorithm. Oh, I explained how to do it in the case of the Poisson process with the shadow line construction, and that produced a partition for me. So just take it as a black box. It takes a random word and it produces a partition. Okay? So it produces a partition that I will. Right. So the picture that I had with the Poisson process was the following. I had the Poisson points. Then I did the shadow line construction, and then I counted something. And then in here, I ended up with a partition. Right? So if I repeat essentially the same, then I end up here with a partition. I'll call it lambda n. I'll draw it in this form. Right? Now, if I take the same box, and then I just strike out the top line, that means that I disregard all letters n that appear in my word. Right? I can always just think of them as invisible. Then I get a word in n-1 letters. And that will then I repeat the thing, and that produces me a different partition. I'll call it lambda n-1. Right? And so it goes up to lambda 1. So lambda 1 is going to be a very simple partition used to obtained from the word where only one letter appears. Right? Okay. So the distribution of the sequence lambda 1 is a Schur process. And the pictorial representation of it is the following. I start with an empty one, goes up to lambda 1, up to lambda 2, up to lambda 3, and so on, up to lambda n, and then from lambda n back to empty. And then I need to put specializations onto the arrows. Then this is a specialization into a single variable a1, a specialization into a single variable a2 up to an, and this here is a specialization that sends the Venn diagram into something that you've seen last time. This is so-called Poncharel specialization, something you get by taking many variables which are small and the number of variables is large. It corresponds, I erased that already. So if you remember my formula, e to the gamma t, the product of 1 plus beta I t, 1 minus alpha I t, then this specialization that sits here, I'll denote it by rho t. It corresponds to killing this part and putting, well, okay, tz here. Okay. So,
but excuse me, in the original definition of Schur process, the diagrams were going like this.
Good point. So in my original definition of the Schur process, indeed, the arrows went like that. Now, if in that definition I take, let's say, the specialization corresponding to this arrow to be trivial, which means that any symmetric function of degree at least 1 goes to 0, then this Q function of a trivial specialization is delta lambda mu. So which means that when I'm putting, if I have lambda, let's say, k here and mu k here, or maybe mu something like that, if the specialization here is trivial, then these two must coincide. Right? So if they coincide, then I can just erase this arrow as a triviality and instead just continue like that. Okay. So by putting some of the specializations to be trivial, I can turn this the up-down picture into any profile I like. And that would still be a Schur process. So for that reason, whenever I'm drawing a picture with arrows like that and putting a Q Schur function on any arrow, this is a special case of the Schur process I started with. Thank you, I should have mentioned that before. Okay. Now then, okay. So then, I was dealing with the longest increasing subsequence, if you remember, which was the optimal path that goes from here and collects the maximal number of stars along the way. Okay. Now, the corollary of this Robinson-Chanstead thing was that the length or the number of stars on the optimal path is the same as the first row of this partition here. Okay. Now, if I go down one step, then the optimizing problem may be slightly different. So then I get paths that may be a little different. But then still the number of stars on that path, on the pink optimal path, is going to be the first row of the next partition, and so on. So these partitions collect the information about optimal paths going to here, 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 or equivalently counting increasing subsequences in the word with lambda letters, or then you kill one of the letters with the word in n-1 letters, and n-2 letters, and so on. Now, here is the upshot, what I'm driving at. Let me call these numbers something. I don't know. Ln minus 1, and so on. So these are the number of stars on the optimal paths. Let's try to understand what happens as the time changes to this vector. How is it going to change? So as the time moves, inevitably there will be a new star appearing somewhere, right? In some row k. So how this star will affect these L's? Well, first of all, the Lk will clearly be raised by 1, right? Because whatever optimal path you have to this moment, there is an extra star appearing, right? Now these ones will be unaffected, right? Because they don't care about stars higher than their level. Now what about higher ones? Well, let's look at the next one. So Lk plus 1. So this one, if it were larger than, okay, so if, let me write it. Now, if Lk plus 1 was greater than Lk plus 1, then I'm claiming it's not going to change. Why? Well, because there is just one star that appeared. The appearance of one new star can increase the length at most by 1. So then Lk plus 1 is unaffected. Sorry, great, stricter. But if it were the same as Lk, then it must go up by 1 new. Why does it have to go by 1? Well, because these L's are clearly ordered, because the optimal path to here collects more stars than the optimal path to here. So if this one gets raised, then this one must get raised as well. It's really, if you don't follow what I'm saying, if you think about it for 1 second, you'll clearly see that this is what has happened. Let me repeat the same thing in a slightly different fashion. Let me put all these numbers, L, N, I'll actually shift them. So I'll add, okay, so these L's are weakly ordered. So if I shift them, they will be strictly ordered. Maybe plus n minus 1, L1 plus 1. I'm going to put them on the lattice. So this is Ln plus n, L1 plus 1. Now these are points in Z, and I'm saying that I know how they evolve. Okay? Now let me say how they evolve. So each of them, each of the points, let's say kth point, jumps by 1 to the right, according to a Poisson process with rate ak. Right? Let's assume all ak's are 1, so with rate 1. So that's just the event of the star appearing in the corresponding row. Right? So each of the particles jumps to the right by 1. And if this position was empty, then this is all that happens. It just jumps, nothing else happens. But if there is a particle here, it tries to jump, and there is another particle sitting there, then it's going to push it. So then it pushes it. And so the eventual location will be like that. This is similar to the exclusion. This is somewhat similar to the exclusion process that I started with. This was introduced in the same paper where the exclusion process was called long range, well, totally asymmetric, simple exclusion process. In fact, the name that we used later in the paper was Stochastic because of the pushing. Now, why is it called long range? This transition here could be thought of as this particle not pushing that one, but jumping over it. Okay, so the recipe is that when the particle tries to jump and there are a few spots occupied, then it either pushes everybody who sits in front by 1, or just goes to the first empty space that it sees. Now, okay, so these were the lambda n1, lambda n minus 1, 1, and so on. So these were the first parts of those partitions. If I look at the last parts of them, then these form this long range TASEP. If I look at these ones, then these form the usual TASEP. It's a little harder to show from the picture, but it's still doable. So somehow, not only I now have the Schur process, which is a static picture somehow, but then by increasing time, there are exclusion processes appearing there. Right? So my goal is really to unite the Schur processes and the time evolution into some meaningful object. Okay, that's what I'm driving. I've so far given examples. Now I'll try to give the general construction. Now, one thing that I would like to do, I would like to actually get rid of this black box of the Robinson-Shenstedt algorithm, of the shadow line construction. The reason I want to get rid of this construction is because it's too fragile. If I try to modify the picture a little bit, nobody knows what this construction would be. Nobody knows what the Robinson-Shenstedt algorithm would be. But the mechanism that I will try to explain now is actually more flexible. And it produces not just this Stochastic and TASEP, it produces a bunch of other systems. They are all solvable in the same sense that I was talking about. Not only that, it will also produce interacting particle systems which are not one-dimensional but two-dimensional, or growth models in 2 dimensions. And many of those systems actually remain unexplored, even though they are interesting. You can see that they're interesting by implementing the dynamics on the computer and seeing how the surfaces grow. You see effects that are interesting, and there are tools to investigate it. It's almost like the experimental science at this moment. You'll see many of the pictures in Gorin's TA session, actually. I'll say more about it. But for now, I'll just want a general construction. So I'll talk about Markov chains on Schur processes. You can see that one way of thinking of what I'm doing, I'm raising the dimensions. First, I started with a single partition, the Schur measures that I'm talking about. That's a one-dimensional object, or point configuration in 1 dimension. I now raise the dimension to consider plane partitions or sequences of partitions, which is a 2-dimensional object. I'm putting a time on that, which is an extra dimension to the picture. And what's important is that I remain in the class of models that are still amenable to something like determinantal process analysis. Okay. Let me just introduce the stochastic matrices on partitions and have the following form. So y and z here are specializations. So these are just specializations. You can think of sets of variables. Lambda and mu are partitions. These are Schur functions. This is a skew Schur function. There is an up arrow here because mu, the landing diagram, is larger than the diagram I start with, which is guaranteed by the skew Schur function here. There is also a downward probability.
Same.
Sorry? What? Yeah. They should be different, sorry. This should be S lambda, yeah. This is the conjugating factor. If you've seen Dyson-Brownian motion, for example, then typically van der Waals determinant plays this role. But it doesn't matter. This is just a definition. So the downward probability is similar. So here the diagrams increase, and here they decrease. Now the fact that these are indeed stochastic matrices in the sense that if I sum either p up or p down in the second coordinate, then I get 1, follows from the two identities on the skew Schur functions I put on the board in the very beginning. Okay. If you think about Toeplitz matrices or determinants of H functions, this is some sort of a Cauchy-Binet, application of Cauchy-Binet. Okay. Now why am I writing them? Well, so that's because these transition matrices act nicely on Schur measures. So this is, if I start with the Schur measure on partitions with two specializations x and y, that will be my notation. And if I act by this increasing thing, then it's immediate. Again, using the two identities that I had on the board, it's a one-line argument. Now this again is going to be a Schur measure where one of the specializations has increased by z. Okay. So you see what happened? It used to be x and y, and now it's x and y, but x has increased by z. Okay. Yeah, in the same way, if I take a Schur measure where one of the specializations can be split in two parts, and then I act with the down probability, then what will happen is that one of the specializations will decrease. So these transition probabilities act nicely on Schur measures. They either increase a specialization or decrease a specialization. Okay? So here is a little lemma. What does this lemma? Well, okay, let me write it down. So the lemma basically says the following. This is a commutation relation on these probability on these transition matrices. Now don't follow the indices, just listen to how I'm going to explain it. So as I said, the increasing probability adds something to one of the two specializations in a Schur measure. The decreasing one removes something. What if I add something and then remove that? Well, that should be the same as removing something and adding it. Right? Now, but that is only true if I start with a sure measure, because I know that my Markov operators act nicely on sure measures. Now, this statement says that it's going to that the two operations will commute if I act on any measure, not necessarily a sure measure. Okay? That's all. So the proof of this thing is a skew Cauchy identity. Everything is somehow based on the two identities of the skew sure functions that I put in the board from the very beginning. Okay? There is nothing else involved. The algebraic structure is all there. Now, why do I care? You know, why are the commuting Markov chains good? Well, I should point out that the transition probabilities given by these Markov chains are fairly complicated. You know, these sure functions are some determinants, so it's easy for me to write the symbols, but if I really want to understand what probabilistically they mean, it's not so easy. So here is something that I learned from a paper by Diaconis and Phil. It's an abstract construction that does the following. Imagine that you have two Markov chains on two spaces x star and x. I'll denote them by p star and p. So these are two stochastic matrices, essentially, Markov kernels. And then there is a map between these. Well, lambda is a bad name. Okay. So lambda here is a stochastic matrix, not the algebra of symmetric functions. And then there is a stochastic matrix that takes you from x star to x. And the whole diagram commutes. Okay. What if I want to build a Markov chain that lives on pairs? So I ultimately want to build a Markov chain that will tell me how to take a pair, map it to another pair, in such a way that when I restrict this Markov chain to the first coordinate, it will give me in some sense the first Markov chain. When I restrict it to the second coordinate, it will give me in some sense the second Markov chain. Well, there is more than one way to do it. Well, here is one way that I'm going to use. It can be characterized by certain independence properties. I'm not going to do that. So I'll decide the following. So I have a pair, one point here and 1 point here. Okay. So then the first thing I'll do, I'll send this point to y without caring about anything else. Okay. So the bottom thing will evolve independently of the rest. Okay. Now once I know where the bottom thing ended, I'm going to use the conditional distribution going from x star to y, using the composition of two matrices to choose what sits here. So I'll write the formula, and then p star x star to y star, lambda y star y, divided by the sum of these two things in y star. Okay. Now this construction has the following property. First of all, if I just look at the bottom row, since the bottom row evolves independently of the top, the projection of this Markov chain to the bottom row will just be p, right? Nothing else. Now, moreover, it turns out that for a class of initial conditions, so for initial conditions of the form, the probability of x star x is some measure in x star times lambda of x star x. Then right. The top row will also evolve according to p star. It's an easy check. I'm not writing it on the board. I don't want to cloud your mind with the computation. It really is an easy check. It's a one-line argument. This is based on the fact, so this is based on the commutation relation, on the commutativity of the Markov chains. Otherwise, I wouldn't be able to do that. Now, what's good about this formula? Well, now if you look at these transition probabilities that I have here, there is a reasonably simple part. So this thing and this thing is simple because eventually the z, well, this will be a specialization into a single variable. Okay, this will be something very simple. Now these objects, the conjugation operators here, are complicated. If you were in Gorel-Shansky's talk yesterday, maybe the day before yesterday, when he looked at Laplacians conjugated by van der Waals. So this is something like a Laplacian. This is something like independent evolution of particles. And this is a complicated conjugation. Now when you substitute the objects like that into the formula, the conjugations will cancel. And this formula will only have the simple objects like that. Let me put it in a little more concrete situation. This was, so I told you that this is a, this is A1 and A2. This was the picture that came out from the random words, and this was a sure process. So the measure was S lambda 1 of A1, S lambda 2 over lambda 1 of A2, S lambda 2 of rho T. I2 can equals to 2. Right? One way to think about this measure, so this is the same, there is a constant. This is the same as taking a sure measure, which lives on top, and then projecting it down with the downward transition probabilities. P down lambda 2, lambda 1. And then, right, with A1, A2. Okay? So now my X star here has lambda 2 in it. My X here has a lambda 1 in it. And this projection has, well, this P down, this thing here. This is a P down. If I now use, instead of P and P star, the raising, so if I use appropriate P ups here, then first of all, the diagram will commute because of the general statement about the commutativity, which is here. And instead of going through the definition, let me just tell you the result. What kind of Markov chain I get as a result. Now this computation that I'm skipping here, not the computation really, but the realization what the result is going to be, will be detailed in the beginning of the recitation, after which the pictures will be shown, I hope. Let me just tell you what's going to be the resulting Markov chain on 3 points. Okay. Why 3 points? Well, because this thing has 2 coordinates, and this thing has 1 coordinate. So here are 3 points. This is my lambda 2. This is my lambda 1. They have to interlace, because otherwise, well, this thing would vanish. And then there is a Markov evolution in continuous time that looks in the following way. Each particle jumps to the right by 1. Independently with Poisson clock. Okay, this 1, okay, I'll assume for simplicity that all my A's are 1, so both A's are 1. It doesn't matter really, otherwise it's not going to be 1, but A with some index. So. All right, so each particle just travels. Okay. There is one unpleasant complication. They can't travel freely. They must interlace. Right? How will that be enforced? That will be enforced in the following way. If this particle here comes close and tries to overcome the bottom particle, now such jump is going to be forbidden. Okay? And just so this is not an arbitrary Markov chain. This is the Markov chain that arises from this construction. And again, if you want to see how, then just go to the next recitation and Vadim will explain. Okay. Now, this is not the only way to violate the interlacing condition. This particle on the bottom may come close to this one and try to overcome it. Okay? Now, if this happens, then the top particle is going to be pushed. And so both of them will move to the next position. Okay? So the general picture that will involve n levels will be a Markov dynamics on a triangular array of particles, where each particle jumps to the right by 1 independently with exponential clock. But then there is something that needs to happen so that the interlacing is not violated, and that happens in the following way. This is the big boss, in the sense that it just doesn't care about the rest, similarly to the bottom level here never cared. So it just moves. What happens if it tries to overcome a particle on top? It just pushes it. Okay? So the big boss is just pushy. It pushes everybody if they're in the way. Now these are sort of smaller bosses in the sense that they will push the particles on top, but if this guy will try to push the big boss, it's not going to happen. The jump is going to be blocked. Now this hierarchy is all I need to define the dynamics. So this defines a certain evolution on the triangular arrays. What are the good properties of this evolution? At any time moment, this is a sure process. Okay? If you look at the evolution, let's say, only of the top row, then this is a random matrix type evolution governed by P up probabilities here, and it behaves asymptotically like a Dyson-Brownian motion, essentially. It actually converges to Dyson-Brownian motion in large time limit in the diffusive limit. If you look at this thing here, so if I look at the leftmost particle in each row, then I claim that the evolution of these particles is Markovian, and it's TASEP. Now, why is it a TASEP? Well, just each particle jumps, and then it gets blocked by the particle in front. That's all. There is no pushing happening, right? So already from this, if you believe that this is like a Dyson-Brownian motion, then you see that these two lines intersect. And so this particle, on one hand, it's a TASEP particle. On the other hand, this is the first particle, the last particle of a random matrix ensemble. So they must have same distribution in the limit, or not even before the limit. And so that explains, in a way, in some sort of a probabilistic way, why the random matrix object should appear in the exclusion process business. Now, if you restrict yourself on this line here, then this is push-ASEP. Because indeed, these particles travel, but now, if one particle meets the other, it pushes it over. So the projection of the evolution on this line is also Markovian, and it's a different Markov chain. And it also must behave as a random matrix object. That's true. Push-ASEP belongs to the KPZ universality class. Okay. Now let me summarize what I tried to explain. What I tried to explain is that if one starts with a fairly general setup of the sure functions, note that here, these specializations in the general commutativity statement are general. There are many parameters in the game. So this object can be, I specialized everything here to a concrete object. That's not necessary. It can be used to define dynamics on various other sure processes, for example, on plane partitions. And I hope Vadim will show pictures of how plane partitions evolve when you run this type of the dynamics. So using sort of fairly generic setup, which consists in commuting transition probabilities, one stitches them together by repeating this Diaconis fill construction. Diaconis fill actually used this construction for 2 levels for a totally different purpose of finding mixing times for something, which gives me a connection to Yuval's talk. So that defines a 2-dimensional dynamics, a dynamics on surfaces, that has nice projections. It has a random matrix type projection, it has the exclusion type projection, but as itself, it's a local 2-dimensional dynamics. So it produces an example of an integrable dynamics on surfaces, which is really the first example that has ever appeared. It actually gives the information about the whole universality class, but I'm out of time, so I'm not going to talk about the universality class of the 2-dimensional dynamics here. So the bottom line is that I hoped to explain how the algebraic properties of the Schur functions that are shared by some other representation theoretic basis, for example, by Macdonald polynomials that I will talk about next lecture, produce a meaningful probabilistic object, but together with that, they carry an algebraic structure that allows this object to be analyzed. So if rather than going from a probabilistic object and then trying to find how to solve the problem, if you do the reverse engineering and start with an algebraic or representation theoretic object, you produce the probabilistic object. If anybody in probability cares about that object, you already have tools to analyze it. Not sure if this is a good or bad, but at least it removes some mystery to me from the question of why certain last passage percolation or exclusion processes were possible to be analyzed using the representation theoretic tools. All right, so next time what I'll do, I'll take, I'm not going to repeat this scheme, but I will tell you what happens if instead of Schur functions here, I use Macdonald symmetric functions, which is a generalization of those. And that will lead to meaningful probabilistic dynamics that is not going to be determinantal, but still going to be analyzable via different tools. And the relevant object is not going to be TASEP or PUSH-ASEP or last passage percolation, but it's going to be the finite temperature random directed polymers and random media. And so in a way, this weapon that I'm suggesting one could use of producing interesting probability from algebra, from representation theory, gave at least one decent example. And that example I'll try to present next time. Thank you.